Einstein's spaceships is an interesting example in special relativity because it uses no maths, just ideas and pictures. Deep in outer space, two spaceships pass each other in opposite directions. Let's take a look.
Here is one of the spaceships with its pointy front end on the left and its square back end on the right. This is spaceship A. The pilot of A is seated exactly in the center of the spaceship, so the distance d from each end to the pilot is the same. Let the pilot be an observer who is stationary in an inertial frame, so his spaceship is at rest in that frame. Here are the two spaceships side by side. The other spaceship we call B, which points in the opposite direction to A. Both spaceships have a device at each end for creating a flash of light when the front of one spaceship passes the back of the other one. We can think of the device as an electrical terminal that is positive at the front and negative at the back. As highlighted on the left, when a positive and negative terminal pass close by, there is an electrical discharge across the gap between them that creates a spark and hence a flash of light. The same flash of light is generated on the right when the front of B passes next to the back of A. Now, light from each flash radiates out in all directions, but we are interested in the two light signals that move alongside the spaceships from each end to the pilot at the center. Note that these signals are not generated by one spaceship or the other, so neither spaceship is a source of the signals. They simply occur in space in between the spaceships. To detect the signals, each pilot has a window with a rear view mirror and a front view mirror. When the two signals reach the pilot's position, they are reflected from the mirrors, so the pilot sees each flash of light and knows whether the signal came from the front or the back of his spaceship. The signal takes some time to travel from the end of the spaceship to the center, so when he sees a signal in one of his mirrors, he knows that the flash that created it must have occurred earlier in time. He can work out how much time the signal took to travel from one end to the center. Recall that according to the second postulate, the speed of light is constant in his inertial frame. The signal travels a distance d, so the travel time is t equals d divided by c. Therefore, if he sees a signal in the mirror now, he knows that the flash that created it occurred at time t earlier. Let's now consider the case of A shown in this diagram, in which he receives two signals simultaneously, which means at the same time. From A's point of view, he deduces that these signals were created earlier in time by spaceship B moving to the right at some constant speed v. Because the signals received were simultaneous, it follows that the flashes that created them were also simultaneous, because each signal traveled an equal distance at the same speed. Flash 1 is on the left and flash 2 is on the right. Now, note that they can only be simultaneous if A and B are the same length. We now follow the sequence of events from A's point of view. A short time after the flashes, signal 2 reaches pilot B because B is moving to the right towards it. During this time, signal 1 has traveled the same distance as 2, but B is moving away from it, so it has to catch up. A little later, both signals arrive simultaneously at A, and finally, sometime later, signal 1 catches up with B. Let's pause to think about this. If B receives signal 2 first and signal 1 later, then B must conclude that flash 2 occurred earlier and flash 1 occurred later. This leads us to the remarkable conclusion that from B's point of view, the two flashes were not simultaneous.
The postulates of special relativity have led us in this example to see that two events that are simultaneous in one inertial frame, that of A, are not simultaneous in another inertial frame, that of B. This is our first counterintuitive result of relativity. Up to now, we have looked at the scenario from A's point of view. Let's now look at it from B's point of view. In doing this, we must work with the basic principle that both A and B must agree on the facts, and these are that A received both signals simultaneously and that B received signal 2 first and signal 1 later.
From B's point of view, because he receives signal 2 first and signal 1 later, it must be that flash 2 occurs before flash 1. Now, the only way that this can be true is if spaceship A is shorter than spaceship B. This may be surprising, but it is the only explanation for flash 2 occurring for flash 1 if the second postulate is valid. A little later, flash 1 occurs when the front of the shorter spaceship A meets the back of the longer spaceship B. A little later, signal 2 arrives at B before signal 1. Then both signals arrive at A simultaneously, which is one of the facts that must be true for both observers. And finally, signal 1 arrives at B.
As you have seen, this example has shown us two remarkable results of applying the two postulates of special relativity, which are that simultaneity is relative, that is, two events that are simultaneous in one frame are not simultaneous in another frame, and that length is relative, because in A's frame, the spaceships are the same length, whereas in B's frame, spaceship A is shorter than spaceship B.